Good day everyone. For today's video, I'm going to discuss all about the logic gates, truth table, and the Boolean algebra. Logic gate. What is a logic gate? A logic gate is the basic building block of any digital system. It is an electronic circuit having one or more than one input and only one output. The relationship between the input and the output is based on a certain logic. Based on this logic, gates are named as AND gate, OR gate, and NOT gate, etc. There are a total of 7 types of logic gates, which we will discuss in this video, along with their truth table or logic table. Followings are the types of logic gates with their symbolic representation: OR gate, AND gate, NOT gate, NOR gate, NAND gate, exclusive OR gate, and exclusive NOR gate. Let's start with first gate, which is OR gate. This is how OR gate is represented. OR gate has 2 inputs and 1 output. Therefore, there can be 2 raised to the possible outputs. Usually, digital signals are represented in zeros and ones. 0 indicates no digital signal, and 1 indicates there is a digital signal. Let's see the logic table or truth table of OR gate. The table representing the inputs and outputs of a logic OR gate. It is called a truth table or a logic table. Since OR gate has 2 inputs, therefore we can name them A and B, and output we will name Y. There can be 4 possible inputs. First input can be A equals 0 and B equals 0. Now, what will be the output? The logic behind OR gate's output is that it shows whether there is a signal in input A or B. Since there is no signal in A or B, the output will be 0, which indicates there is no signal in A or B. Now consider the second case. In this input, A equals 1 and B equals 0. Since there is a signal in input A, the output will be equal to 1. For OR gate, to give an output signal, there should be at least 1 input signal. The third input signal will be A is equal to 0 and B is equal to 1. Since there is a signal in one of the inputs, therefore the output will be equal to 1. And the final input signal will be A is equal to 1 and B is equal to 1. Therefore, the output will be equal to 1 since there is an input signal in both A as well as B. Let's move on to next logic gate, which is AND gate. Similar to OR gate, AND gate also has 2 inputs A and B and 1 output Y. The working of AND gate is based on the mathematical meaning of AND, that is multiplication. For the AND gate, to give an output, both the input A and B should have a signal. Let's see the logic table for AND gate. It can have 4 combinations of input. The first input will be A equals 0 and B equals 0. Since both A and B have no signal, the output Y will be 0. You can also get the output AND gate by doing A into B. Since A equals 0 and B equals 0, 0 into 0 will give the result equal to 0. Second set of inputs will be A equals 1 and B equals 0. Since only A has an input and B doesn't, the output will be equal to 0. Since A into B equals Y, if we put A equals 1 into B equals 0, the output result from this operation will be equal to 0. Similarly, for the third input, A equals 0 and B equals 1, we will have the same result. Since A equals 0 into B equals 1, the result in input Y is equals to 0. For the last set of inputs, which are A equals 1 and B equals 1, we will have the output Y equals 1. Since both A and B are having input 1, this will meet the condition to provide output 1. We can even verify it by putting these inputs into equation A into B equals Y. Since A equals 1 and B equals 1, 1 into 1 is equal to 1. This is the logic behind the working of AND gate. Next, we will see how NOT gate works. An inverter or NOT gate is one that outputs the opposite state as what is input. It has only one input and the output. If you provide input signal 0, the output will be 1. And if you provide an input signal 1, the output will be 0. This is how NOT gate works. Our next logic gate is NOR gate. NOR gate is the combination of OR gate and NOT gate. The output of the OR gate will pass through the NOT gate. Hence, the output gets reversed. That is, if the output of OR gate is 1, then after passing through NOT gate, the output will be equal to 0. Therefore, NOR gate provides output opposite to the OR gate. Let's see the logic table for NOR gate. Our first input will be A equals 0 and B equals 0. The OR gate output will be equal to 0. But as we can see, we have NOT gate. After the OR gate, the output 0 will then pass through NOT gate, which reverses the input 0 into the final output 1. Second set of inputs will be A equals 1 and B equals 0. The output after passing through the OR gate will be equal to 1. Then again, passing this input through the NOT gate, we will have a final output is 0. The next set of input will be A equals 0 and B equals 1. The output of OR gate with these input signals will be equal to 1 after passing the output of OR gate. Through the NOT gate, we will have the final output is 0. Since NOT gate reverses whatever input it gates, and the final set of input signals will be A equals 1 and B equals 1. For these input signals, the output of the OR gate will be 1. After passing through the NOT gate, the final output will be 0. In short, we can say that the output of the NOR gate is opposite to the output of the OR gate. This is how NOR gate works. Let's move on to our next gate, which is NAND gate. As we saw how OR gate's output is passed through the NOT gate to get the opposite results of OR gate. Likewise, the AND gate's output is passed through the NOT gate to get opposite results of AND gate for the same set of inputs. Let's see the logic table for NAND gate. The first inputs will be A equals 0 and B equals 0. The output of AND gate will be 0. After passing this output through the NOT gate, we will have the final output as 1. For second set of inputs A equals 1 and B equals 0, the output of AND gate for these inputs will be equal to 0. After passing through the NOT gate, we will have the final output as 1. Similarly, for third set of inputs A equals 0 and B equals 1, the output of AND gate for these inputs will be 0. After passing through the NOT gate, we will have the final output as 1. For the last set of inputs, A equals 1 and B equals 1, the AND gate's output will be 1, but after passing these inputs through the NOT gate, we will have the final output as 0. Therefore, we can say that the output of NAND gate is opposite to the output given by the AND gate. Next, we will see exclusive OR gate. The specialty of exclusive OR gate is that it gives an output. When there is a signal in only one of the inputs, it will not provide any output signal if both the inputs are 0 or both the inputs are 1. Let's see the truth table for exclusive OR gate. Since it has 2 inputs, there can be 4 combinations of inputs. For first set of inputs, A equals 0 and B equals 0, the output of exclusive OR gate will be 0, since there is no signal in both the inputs. Second set of inputs will be A equals 1 and B equals 0. Since there is a signal in one of the inputs, therefore, the output will be 1. And the final set of inputs A equals 1 and B equals 1. In this case, the output signal will be 0 because for exclusive OR gate, to work only any one of the signals should be high. If both signals are high or low, then the output signal will be 0. Next, and the final logic gate is exclusive NOR gate. As we have seen how NOR gate and NAND gate have been created to get a complement output of OR gate and AND gate. Similarly, the exclusive NOT gate is developed by combining exclusive OR gate with NOT gate. The output signal of the exclusive OR gate is passed through the NOT gate to get a complement output of the exclusive OR gate. Let's see the logic table for exclusive NOR gate. Now our first set of inputs will be A equals 0 and B equals 0. The output from the exclusive OR gate will be equal to 0. But after passing through the NOT gate, the final output signal will be the 1. The second set of inputs will be A equals 1 and B equals 0. Output from the exclusive OR gate will be 1, but after passing through the NOT gate, the final output signal will be equal to 0. Similarly, for input signals, A equals 0 and B equals 1. The output from exclusive OR gate will be 1. But after passing through the NOT gate, the final output signal will be equal to 0. And the last set of inputs will be A equals 1 and B equals 1. In this case, the exclusive OR gate will provide the output signal is 0. But after passing through the NOT gate, the final output will be equal to 1. So we can see that exclusive NOR gate provides the complementary output signals of exclusive OR gate. So these are the logic gates with Boolean expressions. OR gate, NOT gate, NAND gate, NOR gate, AND gate, SOR gate, and the XNOR gate. That's all, and thank you.